My name is Matilda Adwa Kujo. It's my pleasure to introduce the speaker for today, and he's in the person of Dr. Reza Hedayat, who is an associate professor in the Civil and Environmental Engineering Department at Colorado School of Mines. His research focuses on sustainable construction material, non-destructive testing, and I think it's also about and mechanical behavior of geomaterials. He has actually received a lot of awards, including the Early Career Award from the US Department of Energy. And today, he is going to speak to us on a topic, how to transform mine tailings into sustainable construction material. Please join me in welcoming Dr. Reza Hedayat. Thank you.
Hi, good afternoon, everyone. Special thanks to the organizing folks with the invitation to come to this seminar. This is definitely my first time in this capacity, so I'm quite excited. I would like to encourage everyone to please grab your food. That's the top priority. And while you're grabbing your food, I can also tell you a little bit about some of the work we have been doing. So again, thank you for having me here. Today's presentation is related to transformation of the mine tailings into sustainable construction materials. My hope is that by the end of today's talk, you leave the classroom with some additional information about the feasibility of the production processes that would allow us to convert mine tailings to construction materials. So again, a special thanks to folks who are here and for your interest. This is the outline of my talk. I'd like to first start with an introduction and explaining a little bit about the motivation for the use of the mine tailings. Then I would like to take you on a journey of essentially working and evaluating the behavior of some of the mine tailings. For the purpose of this talk, I'm going to focus on some of the tailings that we had a chance to work with from Peru. And then I would like to introduce the three different techniques, mainly about the geopolymer brick. And related to that, we're going to look into the production process and the strength and physical properties of the geopolymer bricks. Then later, we're going to look into a similar process, but for a different product. We will look into the lighter aggregate, the production process for that, and some characteristics of the aggregate, and also their use and performance in terms of the concrete made of those aggregates. And lastly, we can look into the ceramics. Sorry, I'm told that only one button on this remote works, and it's just to advance it. So this is a beautiful picture of Antamina mine, which is located in Peru, one of the major providers and producers of the copper and zinc. So this picture is a really good reminder for all of us about the importance of the mining and the fact that mining engineering plays a major role in our life by providing the minerals and materials that we need for infrastructure, energy, as well as the technology development. So it's projected that the need for minerals and materials will double within the next 30 years. So you can only imagine that the waste of the mining operation also will drastically increase. That waste of the mining operation as a leftover of the operation when the material of value have been feasibly and economically recovered is called mine tailings. And it's projected that we will even be looking at beyond 10 to 14 billion tons of mine tailings to be deposited every year. So if you think about the quantities of the mine tailings, it's of significance. Typically, we deposit mine tailings in two forms. What you see on the left side is the dry stacking after the water has been removed. And what you see on the right side is the slurry deposition in the impoundment lakes, that we have the tailings in the form of the slurry that get deposited behind the dams, and then they go through this process of the retention. And as the material is being deposited, the dam also rises. So you have this process of the continuation of the building of the impoundment lake and the dam that would be retaining the mine tailings. Now, the process of the handling and storage of mine tailings has several environmental, ecological, and economical issues associated with it. Some examples of these processes and these issues are shown here. What you see on the left side is a catastrophic failure of the dam that happened in 2019 in Brazil that resulted in the unfortunate deaths of 270 people and dislocation of millions of tons of tailings. And what you see on the right side are also examples of the air pollution as well as the contamination of the water that would be associated with the deposition of the mine tailings. So here also you can see examples, a statistical evaluation of the records of the different dam failures that have been recorded related to the tailing dams. So unfortunately, tailing dams run about 2 orders of magnitude of higher risk for failure compared to other types of water dams that we have been able to work and engineer over the years. So if we think of the mine tailings from the perspective of the waste and look at the waste hierarchy, obviously, often the easiest solution for us, which is also the least favorable, is disposition and disposal of the mine tailings. And at the top of this pyramid, you can think of the reuse as the most favorable option. And we can visualize and envision many different benefits associated with the reuse of the mine tailings. Starting at the top, we have the creation of the sustainable types of materials that would then allow us to reduce the need for the use of natural resources, limiting the amount of waste production, and hopefully associated with that, we can promote additional innovation and improve the teaching and research capacities in our kind of programs. And hopefully at the end, we can promote different industries related to the production of these construction materials. Oops, let's go back to previous slide. So as a geotech engineer, material engineer, we have some appreciation for some of the materials that come with the mine tailings. As a mining engineer, maybe the materials are considered as the waste of maybe of lesser value, but if we look into the materials, they often contain higher amounts of the aluminosilicates and aluminum oxide and silicon dioxide. So that essentially is a type of material that we would be looking. So from the perspective of a material engineer, the material might have some value. And over the last, I would say 5-6 years, in a research group, we have focused on production of different types of construction materials, mainly from those of the mine tailings in the capacity of the geopolymer brick, lightweight aggregates, as well as the ceramics. So also, since the start of my career at mines, we have been focusing on evaluation of the behavior of the geomaterials. So knowing a little bit about how the materials behave, how they fail, how they fracture, I feel quite comfortable and optimistic that at some point we would have the largest scale application of these materials, as long as we can resolve the issues with the scaling and the higher capacity processing of these mine tailings. So let's start a journey of evaluating the behavior of the mine tailings as related to their typical physical, mineralogical, and chemical characteristics. So what I like to start is a slide showing some pictures of the tailing sites in Peru that we have had a chance to collect some samples. So what you see here is a general map of the Peru, and 2 regions specifically known as Arequipa as well as La Libertad have been the areas where our partner universities were located. So we had a chance to visit the sites. In fact, for each of these, we have had 3 to 5 different sites that we visited. So in this presentation, I'm only going to focus on a few related to Arequipa as well as a few from the La Libertad region. What you see in these images are essentially pictures of the deposition sites. All of these operations were for gold mining. So we had the gold operation as the type of material and the ore that was extracted. So similar to the type of testing that one would do for new construction. So let's say you want to build a new house on an existing ground. The first thing you want to know is, well, what's inside the soil? What type of gradation do you have? What's the chemical composition? And that's exactly the kind of information that we also like to know related to the mine tailings. So first step is to evaluate the gradation. So for that, we need to look into the samples. These are some images of the samples that are shown here with the gradation that we have. So gradation reveals essentially the percent finer versus the different particle sizes for these materials. One of the key safe sizes that we like to always have a good understanding of the person passing is sieve size 200 with the size of the gradation of 75 micron. So that essentially tells us out of the entire assembly of the grains, how much of it is considered as technically the fines, that is the kind of combination of the silt and clay, and how much of it is potentially sand and even larger type of grains. So when you look at the gradation evaluation for these samples, you can realize that these have somewhere like 40 to 60% passing of the sieve number 200. So if I can use the laser option here, hopefully. Yeah, so sieve number 200 as the opening size of 75 microns. So you see that we have 40 to 60% passing of the tailings from that sieve size. But if you look also closely at the portion of the material with the size smaller than 2 micron, which is typically considered for the clay, we don't really have too much of the clay minerals within the material. So the takeaway here is that in terms of the gradation evaluation, most of these tailings that we had the chance to work with are considered as the silty soil type material, sometimes with some amount of clay, sometimes with some amount of sand, but these materials were primarily silty type of materials that we work with. In terms of evaluation of the mineralogical composition, there is a kind of a well-accepted practice where you can use the X-ray device, and by subjecting these materials to millions of the X-ray patterns and looking at the reflection pattern, you can kind of identify some of the key types of the mineralogical composition for these materials. So here, the fact that we do see a lot of peaks in the X-ray pattern can remind us that the materials are highly crystalline, and they consist of some primary types of the crystalline structures. In these samples that we had a chance to work with, we identified quartz as the dominant type of crystal. In addition to that, we also had albite and muscovite that were some rich sources of the aluminum oxide as well as the silicon dioxide. In terms of the elemental evaluation, you also can quickly reveal the elemental composition by doing a basic scanning electron microscope imaging with the EDS. So this would not only reveal the morphology of the grains, but also surface-based elemental composition of these types of tailings. So in the tailing samples, again, that we had a chance to work with, we often saw that we commonly had silicon, aluminum, and iron as the type of dominant types of elements that were available. So some of the takeaways so far in terms of the evaluation has been that silicon, aluminum, and iron are the 3 dominant types of elements within these tailing materials. And often you have some favorable ratio of the silicon to aluminum. In fact, in these tailing samples that we had a chance to work with, the tailing were rich in aluminum silicates, and the silicon to aluminum ratio was ranging from 2 to 3. That often is a good metric as to a good predictor of the performance for geopolymerization and the success of the geopolymerization. But that doesn't necessarily mean that we always will be lucky in terms of having a good ratio of the silicon to aluminum on the tailings as collected and in their raw form. So next, I would like to then also show a typical evaluation of the elemental composition for some of these tailings. If we consult with the Department of Energy's designation for the critical minerals and materials, we often find that from the elemental evaluation, we have some traces of those critical minerals and materials that would be present in these tailings. So again, while being considered as the waste material, we often have some traces of those material that can essentially open up additional venues and opportunities for the further extraction of the value-added minerals. But in the context of the work that we are doing, we are technically ignoring the presence of those critical minerals and materials, and we are really hoping for doing something with the true waste, which in this case is the typical elemental compositions of silicon, aluminum, and iron, as you can see being dominantly present in the evaluation of the elements that are available within the tailings. So again, silicon, aluminum, and iron happen to be the dominant types of elements that are available. So now let's look into some of the processes and the steps that are needed for the conversion of these types of mine tailings to value-added materials. So the first technique that I would like to discuss and present is the geopolymer brick or geopolymer concrete production. So before I dive into the actual process, I'd like to introduce what geopolymerization means. So we need to kind of put a little bit of a chemistry hat so we can go through this, but I try to simplify this process. So the geopolymerization process involves the use of the precursor or the feedstock, obviously in our case would be the mine tailing, as material is subjected to fairly high pH environments, an alkali-rich environment, usually with the exposure to some solutions like the sodium silicate and sodium hydroxide and the mixture of the two, you can facilitate the release of a more reactive aluminum and silicon species. Depending on the ratio of the silicon to aluminum, those released type of species can participate in the formation of the tetrahedral CL8 units. Again, whether you have naturally the proper range that can immediately produce those types of ideal CL8s, or you can engineer the system by providing additional sources of silicon and aluminum, is fairly easy to target different types of connections of the silicon and aluminum species. We usually like to have silicon to aluminum ratio and 3 and higher for the production of the geopolymers. There is a trend that when you achieve those levels, the material not only will be stronger, but also would be more durable. So we usually like to favor that specific ratio, but these materials then connect to each other in terms of the silicon particles, and also would have some aluminum that get bonded to them, and then they form monomers, connect further together, form oligomers, and then these oligomers will go through the polycondensation reaction to generally form the basic backbone and the structure of the polymers that would be able to not only bond the more reactive species, but also the unreactive species. So in other words, you build on the reactivity of some of the small content of your tailings, but then produce cementation for the unreactive content in your material as well. So while this graph is a little bit complex and the process may look like many a step involved, in fact, in reality, the process of making a geopolymer brick, I can present to you that is not really any harder than baking a cake. So if you think about the cake, the fact that you need to have flour and the water to then mix together and form some sort of a paste, we do exactly the same thing. So we have the mine tailings. Sometimes you need to sieve them or grind them depending on their condition. But then the process involves mixing of the mine tailings in the solution of the sodium hydroxide. Upon the mixing, you come up with this mixture that then can be cast inside the form with different levels of the application of pressure. And this material can then form these solids. And these are initially deformable, but then upon exposure to fairly slightly, I would say, elevated temperatures ranging from 40 to 70 degrees Celsius, you can facilitate the hardening of these bricks, and that essentially results in the formation of the geopolymers. Then you can proceed with the evaluation of different characteristics, including the mechanical behavior, microstructure, and durability and leaching performance. So like I said, the process of the geopolymerization in the laboratory, at least on the benchtop scale, is fairly straightforward and is well documented and well experimented in that sense. So what do we do with these bricks that we make? Well, the first thing that we do is to evaluate the compressive strength of these samples. What you see on this picture is essentially a compression testing, where these bricks are placed between the platens and subjected to uniaxial compression. And then we can evaluate and document the performance of these. And we found that the performance and the strength that is achieved is highly linked to the molar concentration of the activator. In this case, we are looking at the sodium hydroxide activator. So what you see here is a typical trend with the increase in the amount of the molar concentration. We often see an increase in the compressive strength. And the strength can be as high as, well, as shown here, 4,500 PSI or 30 MPa. Right now in our laboratory, we are seeing some strength levels that are almost 3 times these values. But again, the success and the performance highly depends on the mine tailings and the kind of aluminum silicate species that are available. But what if we tend to geopolymerize the material, but with insufficient amount of the molar concentration or the chemical type of activator? Well, if we do that, as shown here, we not only get fairly lower levels of the strength, but also the mine tailings remain in their original form. So when the sample breaks, you start to see those powderized type mine tailings that are still available. But when we do the sufficient geopolymerization, the material no longer looks like the original raw form. In fact, you start to see concrete brittle-like type material that can be visible from these images. So the next step in terms of the evaluation has been to see if we have this consistency in terms of the behavior for this material. So we did a lot of testing for many of these mine tailings. realized that the strength that we were getting was not sufficient. So then we went back and looked at the elemental evaluation composition, realizing that in some cases the silicon to aluminum ratio was not necessarily favorable. So we did attempt to amend and supplement that by adding some other types of waste material. So one example of the additional waste is the use of fly ash. Fly ash is a rich material in terms of the aluminum and silicon species that are a lot more reactive. You can think of the tailings generally as being unreactive or less reactive compared to something like the fly ash, which has a lot higher amorphicity and less crystalline structure, as you can see from the XRD pattern. So by simple mixing of the solid content of the mine tailings and the fly ash and repeating the process, you can and would have an opportunity to produce new geopolymers that hopefully would have some improved performance and characteristics compared to the tailing only based type geopolymers. So we did that. We evaluated the mixture of the tailings and the fly ash in different percentages of addition of fly ash. And I think we went up to 20% addition of fly ash while still maintaining that high percentage utilization rate of the mine tailings. So again, with the 20% fly ash addition, we only had 80%. Well, we had 80% of the tailings that were used in that production process. So looking at the SEM evaluation of the tailings and the fly ash, simply recognizing that the fly ash has fairly higher amount of the aluminum and silicon that can then help to facilitate a better connection and development of the network of the polymerization. So we have also this understanding that the silicon to aluminum ratio would be a key determining factor that can be favorably adjusted by the addition of the fly ash. So the production process is as the same as before. You just mix the fly ash with the tailing, and then you mix it with the activator, and then go through the casting process. Here are the pictures of the specimens that we made, ranging from 0% addition or supplementation with the fly ash all the way to 20% addition of the fly ash. So all of these samples kind of look visually the same. They all look like solid after they completed the curing process. And by the way, I should have mentioned that the curing process is usually 1 week long. So we put the samples in the oven, first at the 40 degrees Celsius, followed by about another 7 days of the curing at the 70 degrees Celsius. So that's what we did for these steps that are shown here. In terms of the influence of the fly ash addition, we documented that when the samples are tested, in terms of the addition of fly ash, if we consider the control with 0 amount of fly ash, we see favorably improvement in terms of the strength of the sample and the general stiffness improvement for these samples, if you look at them in terms of the relationship between the stress and the strain. But looking at the peak values and plotting them as a function of the addition of the fly ash, you can see here that with the addition of the fly ash, we generally have an improvement in the compressive strength of these samples. So if you want to kind of visualize a virtual line as the bare minimum strength requirements for these bricks that we are making, we usually consider 20 megapascal as the requirement for the strength. So one can argue that, well, if you get 15 MPa of compressive strength, that's probably insufficient. But as long as you can hit consistently 20 MPa and higher, ideally higher, then your geopolymerization has been successful for the purpose of the brick manufacturing. So what we saw here in this scenario was that even as low as 15% addition of the fly ash can drastically increase the compressive strength of these cubes compared to the control. We saw about 75% improvement in the strength when we used 15% addition of the fly ash. And yes, you might still have some additional improvement, but at least it wasn't very visible or evident to us that justified the additional use of the fly ash. So we kind of consider the 15% as sufficient amount of supplementation for these specific tailings. Next, we can look at the fracture behavior and the broken samples of these tailings at different percentages of the fly ash. So again, kind of a basic visual observation that all of these samples tend to behave similarly, at least visually, they all look very similar. They all look like a broken concrete sample that maybe even look nicer and more beautiful given the kind of background color that the tailings came in. And then we looked into the process as to why the additional presence of the fly ash, let's say the 20%, didn't really make much improvement in the properties. And we realized that as we exceed the 15% fly ash, any additional amount of fly ash just simply remains inert and intact and untouched, and does not necessarily contribute or participate in the geopolymerization reaction. So any amount of the unreactive content even from the fly ash can necessarily be bad thing, maybe because of the fact that you are incorporating fly ash as a commercially available type material. So in this case, we were able to look into the SEM micrographs and visually confirm that 15% was the ideal optimum range because it still allowed for geopolymerization of the fly ash, but in the case of the 20%, we had some amount of the fly ash that was present in the original inert form and did not really participate. For those of you who are familiar with the scanning electron images, fly ash is a very distinctly visible type material. If you do have the powders of the fly ash and put them under the microscope, you realize them by these beautiful spherical particles that are out there. So this is a kind of a distinctive feature of the fly ash that was also visible from our images. We then look into the XRD to then identify some evidences of the sufficient and successful geopolymerization. So one of the first things that we saw was that from the XRD patterns, we saw a general trend of reduction in the intensity of the quartz or the silicon dioxide. So in this case, we saw that these intensities started to decrease as the percentages of the fly ash was increasing. So first evidence was that, well, this is a good sign that some of the existing quartz that was otherwise observed in the original raw mine tailings was being consumed and participated in the geopolymerization. We also saw at the 2 theta of about 28, the peak for the calcite that was also intensifying. So we saw the increasing the calcite presence as a result of this geopolymerization. So we took those two evidences as indicators of the successful geopolymerization for these materials. All right, so, but evaluation of the behavior of the material would not be complete only after we do the compressive strength testing. In many cases, it's very important to evaluate the behavior of the material and the resistance to fracturing. So that is a type of a test that we consider as a fracture mechanics type testing. If I want to find an analogy to this, is like that little chip that you get on your windshield, and you ignore that chip, and eventually after maybe a season of the winter and then wetting and drying, that chip starts to grow and turns into a big crack that has grown, right? So that tendency for the chip to become a major crack is related to the tendency of the material to resist the fracturing or allow for the fracturing to happen. So we can evaluate that resistance or tendency by intentionally performing fracture testing. So what we did in this scenario, we did the 3-point bending test on semicircular specimens. These specimens were cast the same way as before. We put them on 2 rollers and then we apply the load at the top. This facilitates the formation of the mode 1 fracturing from the tip of the existing notch. So think of this notch that we artificially introduced in our sample as like your windshield chip. And that's the point of concentration and initiation of the cracking. Like this mode of loading, we can promote the fracturing and evaluate how much force it takes. What are the characteristics of the fractures as they're generated. So we did also apply a technique called digital image correlation. Is anyone using digital image correlation in this audience? I know mining engineers love that technique. If you're doing experimental work, you probably at some point will look into this. So the beauty of the digital image correlation is that you can have a camera that is mounted on the testing setup quite far, in fact, in some cases intentionally far from your object with no physical touching or contact between the camera and the object, but then you can take images of your object, feed them into a software, and then based on the minute changes that can be only observable to the algorithms implemented in the DIC, then you can get a full profile of displacement and strain for your sample. So that allows us to get a full picture of the deformation pattern for the sample without even touching the sample or installing any type of sensors on the sample. So it's truly non-destructive way of evaluating the characteristics of the fracturing for the material. So in that case, we noticed that with the increasing the amount of the fly ash, the force or the fracturing levels were increasing. And if we do apply the fracture mechanics concept and get the mode 1 fracture toughness for the material, we did notice that with the increase in the fly ash content or amount, we have had naturally an improvement in the fracture toughness values for these materials. We did compare these values with the fracture toughness of concrete and realized that the fracture toughness values were also pretty similar and within the same range as a normal concrete. So we not only met the compressive strength of the concrete, but also achieved similar level of the fracture toughness, like the concrete material in our geopolymer bricks. But having evaluated the fracture behavior, while important, was still not sufficient, because in many scenarios, we would hear from mining industry folks that they are often concerned about the potentials for these materials to leach out some of the heavy metals and contaminants. So let's say you make these bricks and they're looking pretty nice. 10 years from now, they start to fall apart and you have all of this hazardous content that is getting released. So we were quite interested in also evaluating that as well. So, but before I show you some of the results, I'd like to again make the point that in some scenarios, your mine tailing in the original form may only give you fairly low levels of strength for your geopolymer bricks, maybe let's say in the order of 10 megapascal, but it may only take 15% of different types of waste to be then supplemented with, for example, metakaolin, fly ash, and slag. In all of those cases, only adding 15% of your solids in the form of those supplements can double or triple your strength values. So that's a good reminder that sometimes, even if you document some deficiencies in the strength, the solution would be fairly simple and inexpensive in the case that you can increase the compressive strength of the samples. So what did we do to evaluate better the potentials for immobilization of the heavy metals and contaminants? Well, as you can imagine, a typical test would be to submerge the samples inside a container and keep tracking of the amount of leachates for a longer period of time. So in this scenario, we did testing for about 63 days. Every single day, we collected samples of the leachate, sent it to a laboratory, evaluated the ICP and the elemental composition of the leachate, and then fed it to some models to then evaluate the parameter known as the leachability index. There are several standards, mainly written by Canadians, that consider the successful and safe reuse of materials when this leachability index is 8 or higher. So we did confirm that for many of the heavy metals and contaminants that we were having in our tailings, in fact, the leachability index was sufficiently high. I would still think that according to the standard, the value of 9 or higher would be considered as required. So I think I should mention that the arsenic was one of the few contaminants that we reached a value of 8 to 9. So additional work definitely is warranted to make sure that the material would in fact achieve higher level of the leachability index when tested in this scenario. So that was essentially a summary of the evaluation of the work that we have had so far, but we are working towards additional larger scale production of these materials. So if you look at the industry and the practices, you realize that for the brick to be made at the larger scale, you need to have a big extruder where you can extrude the material at the large capacity. We are looking at like thousands and tens of thousands of bricks to be made on a daily basis. So obviously the process that we have at the laboratory is not really scalable, but we are looking into some alternative solutions where we can essentially develop an extrusion-based technique for the production of these bricks at the later time. So that's essentially what we are focusing on, and in terms of improving the surface texture and the extrudability of the material. The next type of, so quick overview of how the material can be optimized in terms of the extrudability with some really basic tools and techniques, but obviously additional work is needed to be able to make the material really smooth and hopefully scalable at some point. The next type of technology that I'd like to introduce briefly is the lightweight aggregate production that we would have. For this type of materials, we are looking into, again, the use of the mine tailings as much as possible, but now it's a slightly different process where we would like to make aggregates for potential use in the concrete. So in this process, we have generally this motivation where obviously lightweight aggregates are important for our industry. We use them in several different application areas, mainly for production of the structural lightweight concrete. You may ask, well, what are the motivations for the production of the structured concrete that would have lightweight aggregate compared to the normal weight aggregate? Well, the primary reason is the cost as well as the density or the unit weight for the concrete. So imagine if you have a high rise that you envision significant quantities of the concrete to be poured and then placed. If you can manage to maybe lower the density of your concrete by 30–40%, that should translate easily into maybe a smaller foundation, cheaper foundation that you eventually will have as well. But in addition to that, there would be also some superior characteristics for the lightweight concrete in the sense that it's better in terms of the soundproofness as well as the thermal insulation for your buildings. And that's the primary reason that you can see in the market, the general rise in the demand and the market size for the structural lightweight concrete. Since 2019, the market has been valued at almost $40 billion. We are on track to hit $60 billion in just a few years for this type of material. So then you may ask, well, okay, so what are the issues currently with the existing practice that may motivate us to look into the use of mine tailings as an alternative? So currently the lightweight aggregates are produced by extracting natural shale and clay, subjecting those shale and clay material to excessively high temperatures around 2,500 degrees Fahrenheit. So you need to use a kiln and sinterize your natural extracted type material. And that process is very expensive and with also a fairly high carbon footprint. So imagine talking with the different producers, one of the major pain points that they have is that out of the total cost of these lightweight aggregates that they produce, almost half of it goes to the cost and covering of the utility expenses for these materials. So these are fairly expensive, environmentally unfriendly type of material. So we had this motivation, and as the first research group, we started to look into the process of the production of the aggregates from the mine tailings. So with a small tweak in our process where we are still using the alkali activator by simply spraying the alkali activator on the pelletizer, we were able to produce the aggregates in the form of the pellets that then would undergo the curing process and then incorporation into the concrete. So fairly similar in terms of the chemistry for this whole process, where the mine tailings are often mixed with some additional supplements, then mixed with the sodium hydroxide solution that gets sprayed on the pelletizer, and the material then goes through a curing oven, and then you will be left with the finally cured and ready to use type of a lightweight aggregate that can be incorporated in the structure of the concrete. So one of the key questions we had was, well, first, are these aggregates of sufficiently higher strength that can be utilized in the concrete? Second, how does the concrete then behave using these aggregates as the primary type of coarser material being used? So again, another picture or view of the pelletization effect. You can see here that the spraying is being done on the pelletizer. In this case, the material is granulating. And then if you give it sufficient retention time, the material can then sufficiently pelletize. I do need to note that this pelletization process that we follow is not necessarily adoptable at the industrial scale. We know that the big pelletizers in the large scale need to only operate for 3 to 4 minutes. We call this time as a retention time. So your material will need to be dumped into the pelletizer after 3-4 minutes need to exit the pelletizer. So our process currently lasts about 30 minutes. So we need to do more work so we can improve this process. But at least the fundamentals are there where we can see the production of the lightweight aggregate in that sense. So what we did was to document the characteristics of this aggregate and then incorporate them in the matrix of the concrete and then proceed with evaluation of the concrete characteristics. We did this by coming up with a basic mix design for the concrete, added the aggregates, and then came up with these cylinders. After curing, we proceeded with the testing of the compressive strength of these cylinders. There are existing ASTM standards that require us to hit the minimum of 28 megapascal at the 28 days for this structural lightweight concrete. We did achieve 44 MPa using the tailing-based aggregate. So we were comfortable in the sense that the strength was achieved fairly easily, but we also were concerned about the potential freeze-thaw damage, especially imagine if you're using this lightweight aggregate in Colorado that would be subjected to freeze-thaw cycles. So we wanted to see how the freeze-thaw may potentially affect the performance of these samples. So we made some beam samples, put them into a chamber, and then exposed it to freeze-thaw. This test involves applying 300 cycles of freezing and thawing. And by doing so, you can evaluate the degradation in the dynamic modulus of the material as a measure of the damage. And as long as your new dynamic modulus is at least 70% of the starting point, then the material can be considered as successfully passing this test. So we did this type of testing, and to our surprise, the value of the reduction was only about 10%. So we retained 90% of the original dynamic modulus, therefore considered the tailing-based aggregates as successful. And to our surprise, the control samples that we made from commercially available lightweight aggregate, they all failed and crumbled by the end of the test. So we even had the kind of bragging that tailing-based aggregates were superior to those commercially produced lightweight aggregates that you could buy from some of the nearby facilities. So that's essentially the evaluation of the aggregate, but obviously more work needs to be done. So this can be adopted at a larger scale. And right now we are also evaluating another type of innovative approach where instead of using alkali activator and the solution of that, we are just simply using existing some cementitious materials, starting with the Portland cement as the cold bonding agent. So my student Amin is here. If you have any questions about the cold bonded type aggregates, please ask him, as he has been working on the challenge of producing aggregates that would also be lightweight in terms of the structural application. So, but a fairly similar process, but we believe that this would also have potentials for adoption because first, you don't have any need for alkali activator, which is generally a hazardous type of material. Second, the process of spraying is fairly simple and you're just spraying water to an already mixed solid powder of the tailing and the cement. And we have gotten some encouraging results with only using 30% of cement, still 70% of the tailings used for this application process. And lastly, I'd like to say a few words about the care technology around the ceramic tile production. So ceramics are the type of a material that are developed based on the sintering practice of the original raw material that needs to have some rich contents of different types of minerals and different types of components, but we generally think of the feldspar, metakaolin, as well as the silica as the primary types of raw constituents. For ceramic manufacturing, they often need to be finely ground and finely reduced in size. So first, you need to extract the material naturally. Second, you need to grind them and pulverize the material. And then you need to then mix them with the water, put them into a forming application or extrusion, and then sinterize the material. So one of the motivations we had was that, well, first, tailings often have, either in their sole form or in the blended form, all of these constituents that we like and need for ceramic manufacturing. And second, tailings are already finely powderized type material. So you not only need to eliminate the step of extraction, but also you can save money in terms of the need for grinding your material because it's already powderized. So all you may need to do is to further grind it as needed, and then remove some of the barriers like the sulfate content, and then proceed with the addition of the grinding and addition of the lubricants, application of the forming to come up with your green ceramic to then go into a sinterizing oven, and then eventually you will have your sintered ceramics. And you can proceed with evaluation of different characteristics for these materials. So that's exactly what we did. One of the key questions when it comes to sintering of the material is the temperature at which you can apply the sintering effect. So we did explore different temperatures. Here we had starting with 1,000 degrees Celsius all the way to 1150. The challenge was to identify the optimal temperature for the successful ceramic production that you would provide with the highest density as well as the lowest porosity. So if you do a comparison among the different temperatures that we explored, clearly you see that the 1100 was the best performing because it provided us with the highest density as well as the lowest amount of porosity for these materials. So we adopted that for the production. We also confirmed through the X-ray diffraction evaluation that the raw materials, in fact, the muscovite, pyrite, and the gypsum, were all transformed into a new phase known as hematite through this sintering step. So they were no longer present in the original form, and hematite was formed in addition to the quartz for all these materials. We were also interested in evaluating, in addition to the strength, the fracture behavior of these materials. So we did fracture testing, again, using semicircular bend type geometry, and confirmed the fracture toughness for these materials and looked into the size of the fracturing. Again, the beauty of the digital image correlation is that it provides you with the entire profile of the strain and the deformation on the surface. So by doing so, we were able to document and confirm that these tailing-based type ceramics had also successful and similar fracture behavior to the sintered-based ceramics from natural resources like sand and clay. And yes, so that's essentially where the research stands at this point. So we are hoping to find ways that we can take this to a next step and be able to apply the same methodology at the larger scale. So, and also in addition, we are working on developing some supplementary cementitious materials from mine tailings, again, because of the presence of the aluminosilicates. Sometimes all you need to do is to finely grind your tailings and incorporate them in the structure of the concrete with the hope that you would have tailing-based concrete additives that would then facilitate better formation of the cement hydration products and improvement in the durability of your concrete. So that's another type of a track that we are working on. So if I want to summarize some of the major takeaways, it would be as follows. Mine tailings rich in aluminosilicates can be activated and converted to different products, including geopolymer concrete, brick, lightweight aggregates. The produced geopolymers often show high levels of strength, and sometimes they are deficient in terms of the amount of the aluminosilicate species. So it would be important to adjust that with the hope of achieving a better cell structure for your geopolymerized material. We showed that the lightweight aggregates are also viable to produce, and they can meet the ASTM standards for even structural applications. In some scenarios, sulfidic mine tailings can also be successfully transformed into ceramics, but that process requires us to get rid of the sulfate, maybe through a calcining process, but then proceeding with the grinding, forming, and sintering of the material. And we are hoping to expand our research portfolio and work into the additional steps that would allow us to explore the larger scale production of these. Eventually, we are hoping that we would see a paradigm shift in the way that we can treat and process the mine tailings. So with that, I'd like to share some of the existing resources and papers that we have published over the years. Happy to share any of the copies if anyone is interested in a specific technology. And also thank our sponsors, mainly the Institute for Initiatives in Latin America, the State of Colorado Advanced Industries, and the Tailing Center, and you all for your interest and being here. Thank you. Yes.
I have a couple of questions.
Sure.
First, thank you for the presentation. That's all. I have two questions. The first one is related, like, about the proposed concrete. Is it defined for a specific type of structural element? I mean, like columns or beams, since I haven't seen this structural test happening out there. And my second question is regarding that durability tests. They only focus on this leaching behavior of the metals, or they go far beyond just to simulate long-term service for each kind of element?
Yeah, great question. So related to your first question about the application area for these lightweight structures, so there is an ASTM standard that designates what type of aggregate can be successfully used for production. But as soon as you have confirmation or evidence that your aggregate does meet the ASTM standard, then the application areas are kind of limitless in the sense that you can choose to use it for many structural applications. You can have the beams, columns, bracing elements, foundations, and so on. But there is a very important step that you need to document and demonstrate that the aggregates are meeting that ASTM C33 requirements. Related to your second question, that's also a very interesting one. Unfortunately, while we work on these relatively newer areas, we also suffer from the fact that there are not well-established standards. So we don't currently have an existing standard that would then provide us with guidance as to what is expected of the geopolymer bricks. So we tend to kind of all randomly come up with these different testing programs that we can evaluate, but unless we come together and develop a standard, we won't really have a good way of documenting the requirements for performance, whether now or down the road. Please.
Thank you for the presentation. Question is, some things contain some heavy metals and some can be radio and harmful. So, are there some mechanism in place to try to filter off this heavy metal for use?
Yeah, it's a great question. So yes, understanding that tailings are often waste and not really fully controlled, they may have some heavy metals and contaminants. I think at the point where we are still developing technologies for the immobilization, one of our safer approaches would be to first try to figure out what are we working with. If we come across a tailing source that, let's say, has higher amount of sulfates and some good, higher quantities of the more reactive contaminants, that probably is not the good candidate for this stage of research. Maybe we can look into some potential less harmful, easier to work type tailings that we can develop further the technologies, but then come back and maybe try to reprocess those tailings to get rid of those harmful elements before further utilization.
Why I'm saying this is just that I mean, some of the researches that I did in Africa for coming out here, that some most things they are very active in nature. And
Yes.
so far we abandoned them there and we
Yeah.
are unable to use them.
Yeah.
And you know, they're constituting nuisance by that residences have been building around those abandoned mine-tailings. So thinking of what can be used, I mean, what can they be used for? Will it be upon ever? So that's
Yeah.
why I am.
So yeah, the great question. I have to actually say that this kind of gets outside the scope of expertise that I have. Maybe Jehan can help with the mineral processing steps that would be needed for really working on those materials. But I would definitely consider those as like maybe secondary choices that you still are not there. Yes.
One troublesome mineral whatever we have in this kind of things is sulfur. I didn't say it in the whole scheme of things associated that. So I never made mention of this.
Yeah, so yes, correct. The tailings that we collected from the Libertad region, south, well, actually north of Peru, some of those had high sulfuric content. So we had this challenge. I think in some cases they even had 20% of the elements sulfur for those tailings. So we use them for ceramic production, but that required us to go through this calcining step where you need to expose the tailing to 700 degrees Celsius to try to burn off the sulfur. You probably cannot fully get rid of it. And I would imagine that this is not a very environmentally safe process because you still have these hazardous gases that get emitted. So while working and successful at the laboratory scale, I do believe that additional processes need to be in place to be able to reduce the sulfate content for these samples. Yes.
About the factor, if this is supposed to be implemented, is it going to be like for tailings that have been closed, or is going to be able, like the other having to come directly from the plant with a slurry or paste or whatever, and then use it for the geopolymer? That's one. And then also two, if you mentioned that the chain and I think you spoke about having a cash and all about if it's used for like flexible pavement, and it rains and there's snow and all of that, but a bigger surface area is exposed. Is there also not that possible to change giving you a lot of cash?
Yes, yeah, great questions. First question related to what type of tailing can we work with, or do we have a preference? I'm very curious to hear from mining engineering folks and maybe faculty or students working in this area. My understanding of the legal aspects is that if a tailing has already been deposited and if the mine has already been closed, it would be a really big challenge and task to go dig it up and start using that tailing. Now, general observation is that you touch my tailing, you bear responsibility for it, right? So that's the kind of approach. So that essentially means that the tailings already deposited in closed facilities are out of the question until we come up with some maybe legal improvements that we can come with ways to work or maybe collaborate in terms of use of those. But the freshly produced tailing is always an option where you can have the processing plants in place that you can work with the production of the value-added materials from this. And you also had a very valid point for in your second question as to what if we have a scenario or application area where potentially can be even more problematic? And I have to say that yes, it's a very real case. But again, keep in mind that yes, working with tailing, we have this extra level of curiosity or kind of consideration that there would be potential issues. But again, keep in mind that the other types of geomaterials like the sand, clay, and the rocks have gone through the similar process of weathering over the years. So they may have similar original type of chemical composition that they're otherwise being used for the process of the paver manufacturing and so on. So many of our existing processes that use natural resources have similar type of behavior in the raw material to the tailings that now we are kind of scrutinizing maybe beyond the needed levels.
I was just wondering, for your geopolymerization process, you said it usually takes 1 week. Have you looked into any way of shortening that time span and what effect that would have on the
Yes, great question. There are ways that we can incorporate additional supplements And by doing so, you can shorten that. So there's always this fine balance as to what is the carbon footprint of the curing step compared to the original feedstock. Even within the time frame of the 7 to 10 days that we consider as necessary, we have done some cost evaluation as well as there's a life cycle analysis. We have confirmed that the CO2 footprint of the geopolymer-based bricks is almost half of the sinter-based bricks. So we are looking at the process, even with that bit long of the curing that is needed, just because of the low temperature requirements. Again, you don't need that 2000-degree-Fahrenheit temperature, right? So you only need like maybe 40 to 60 or 70. So you look into the process that's much more environmentally friendly and cost-wise is almost 2/3 of the sinter-based. That's right. So we are still in a pretty good spot, but absolutely I agree with you that we like to accelerate this process and make it maybe even faster. But there are ways that we can do that, and only requires you to add additional supplements that would be reacting faster. Things like methylcowline or kaolin.
But increasing the heat would do anything?
Not necessarily no processes. No, it doesn't really affect. If anything, it would actually make it worse because then you start to cause evaporation of some of the solution that you otherwise want to react with your kit. So you start to have a lot of pores in your circuit.